So good morning. While they set up the presentation, I was just very fairly introduced by Costas. Thank you. Actually, pretty amazing audience because you don't hear often in the corridors. There's the safety course. I can miss it, or something like that. It's something that people usually try to avoid. But I got some good news today because first, we don't have to be compliant with regulations. So today, not in this talk, so that we're going to skip most of the boring part, which is about regulations. And the second good news is that there's not a single equation in this talk. So it's going to be easy. The first thing you will see it then in the slide, but you know what is from actually I lied to you because I said that we were not speaking about regulations, but we will. Here we go. So, okay, very good. So this is a picture that I stole from Wikipedia, but it's pretty cool. It's quite a comprehensive list of lasers. And you see there that it covers from, you see there, about 100 nanometers to 1 millimeter of wavelengths. Okay. This is what's in the law is defined as optical radiation. Whatever is longer than 1 millimeter is considered electromagnetic field. And what is shorter than 100 nanometer is considered non-ionizing radiation. You know what's the difference? Anyone knows what's the difference between ionizing and non-ionizing radiation? Actually, ionizing radiation like X-ray or nuclear decay is a radiation that has the power to steal electrons from atoms and in principle can modify cells and biological tissue like DNA, biological molecules like DNA. So if the energy of the photons is extremely high, so wavelength is lower than 100 nanometers, as a convention, we say that that's ionizing radiation. Optical radiation, it's not. And also, electromagnetic fields are not. So then you see there's quite a plenty of laser sources that can range for, I would say, almost all the optical spectrum. But as I told you, I lied to you, so we are speaking about regulations. When we speak about lasers, we have a classification for the law. So most of the people don't even know there's a classification. Some people know that there's a classification and they think it's made of 4 classes. Actually, this was changed long ago. And in terms of safety, lasers can be in 7 different classes. Class 1 means it's a safe laser. So in reasonable conditions, you're going to use it pretty comfortably. You're not going to hurt yourself. Actually, it's so. Yeah, that's unlikely to be a class 1, indeed. So I will say this because most of these laser pointers are not placing themselves there, but they're. This doesn't work. Actually, it doesn't matter. It is, I think. Okay, no, it was my incompetence, actually. It's green, it's beautiful, yeah. Oh, yeah, it's more well absorbed, indeed. But actually, most of these laser pointers are in this class, okay? So, class 1 lasers are almost non-existent in principle. There are not many. But it's useful because if you enclose a more powerful source in actually an enclosure that doesn't allow radiation to come out, you're going to classify the laser as class 1. Class 1M is actually the same thing, but it says it's going to be safe if you're using it normally with no optics. Then if you use optics, we are not going to guarantee that, okay? Class 2, it's a peculiar class because it's just about the visible range. So lasers that emit from 400 nanometers to 700 nanometers. And this is quite an important point. they are safe because protection is afforded by aversion responses, like blink reflex, your eyelids closing or your head moving, okay? So that means, since our aversion reflex is usually about 0.25 seconds, it means that they are not going to be dangerous for an exposure which is lower than 1/4 of a second. Class 2M, or you know already what's the point about it. It's going to be safe in the visible unless you use some optics, and then we cannot guarantee. Then class 3R, the definition for the law is pretty curious in this case, because it says, okay, they are emitting in this range, but it says they are intrabeam viewing is potentially hazardous, but the risk is lower than another class. And this is actually what the law says, so it's pretty, hazy as a definition. And then we get to the, let's say, vast majority of lasers, which are 3B and 4. Class 3B lasers are considered safe for diffused viewing. So if I put this laser on the wall, there's going to be diffusion, and that is going to be safe if it's a 3B laser. But it's not safe to put it in your eye directly. While class 4, it's the more complicated part, because they are considered dangerous for direct viewing, diffused viewing, and they also give you a fire hazard. Actually, whenever you have these kind of lasers, you need a guy like me, so a laser safety officer, to carry on the laser risk assessment. This is the last regulation slide, I promise. You see, it's the maximum allowed continuous power for to be allowed for a laser to stay in one of the classes. Okay, so what you see is that it's actually impossible. This is 3B for whatever laser above 500, 600 milliwatts to be in a class which is not 4. Okay, so then whenever you're going above 500 or 600 milliwatts, that laser is going to be potentially is going to make potential fire hazard. It's going to be dangerous for intrabeam viewing and dangerous for diffuse reflection. Actually, this is not the only requirement you have for lasers to stay in a class, and it is not the only requirement that you have to take into account when you're making risk assessments regarding laser. It's of course the most obvious, okay? So if I have a very high power laser, like 1 watt, and I want to bring it to the safe level, so below class 1, let's say that, I don't know, we are here at 900. So 1 watt, this is 1 milliwatt, then I should bring it down of 3 orders of magnitude in power, right? So then one may think, if I get a filter that has an optical density higher than 3, you know what's optical density? Very good. For those who don't know, optical density is the logarithm of 1 over t, where t is the transmittance. So that means that optical density 1 means that 10% of the light is going through the filter. Optical density 2, 1% of the light, and so on. So then if you take an optical density 3 filter on a 1 watt laser, you're going to be there, right? I mean, it's just going to come out 1 milliwatt. Wrong. Because this is totally wrong, because this is not the only parameter that you have to take into account. Indeed, in real life, usually filters are 1 or 2 orders of magnitude higher in protection than this. And this is the reason. When you're considering a continuous wave laser, let's start from the continuous wave laser actually. The parameter that play a role in let's say in the dangerousness of the laser are of course power. This is obvious. But also the spot size. You can guess that if I have a spot size like this, not all of it will go into my eyes, for example, because my head, my iris, and everything else is going to be actually a mask for that. So spot size is also important. Or a very, 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 very tiny beam, it's going to go all through my pupil. The wavelengths, of course, you may argue that different wavelengths are differently absorbed by different tissues. So then, of course, the color of the laser is going to give different trouble or different damage. And also divergence, because a very well collimated beam is going to be focused much better. So then it will make a smaller focus on the retina, and it will make more damage because actually the radiant exposure, the term is the radiant exposure, is going to be much higher. Okay. These for continuous wave lasers. When you get to pulse lasers, things are a bit more complicated because the number of parameters playing a role is quite different. Of course, you still have the spot size. Of course, you have the wavelength, the average power, but then the pulse duration and the repetition rate are going to play a role too, because depending on the repetition rate, for example, you may have time for biological tissue to thermalize after it was excited or not, for example. And the pulse duration and pulse energy themselves can play a role because, let's say as a rule of thumb, a gradual eating of biological tissue is going to give coagulation, while an instant heating is going to give you vaporization. Okay, so this is a totally different process that happens to biological tissue because of the laser. Now, okay, this is pretty obvious. What are the target organs for lasers? One is eyes, of course. What's the other? Liver, pardon?
Skin.
It's skin, indeed. Let's start from the eyes because it's way more complicated. Skin is easier to be discussed. So this is actually a very gross approximation, but you know how painful it is to look at the sun directly, right? I mean, you cannot hold for, I would say, 1/4 of a second, in principle. This is the radiant exposure given by direct exposure to the sunlight on the retina. It's 10 to the 5 watts per square meter. If you take a really tiny laser pointer, 1 milliwatt helium neon at 633 nanometers is going to give you this number. So it's about 30 times higher than the sun. And it's a very, very tiny laser. In principle, this could be classified as class 2, in principle. Okay. I said that this is a gross approximation because it depends on many factors. For example, how big is your pupil? How your eye is going to focus. Usually it's 17 millimeters, but depends on from person to person. And actually for this calculation I assumed that when you're looking at the sunlight your pupil is pretty close, which is pretty a fair assumption. However, this is one of the reasons why lasers are so dangerous. Even a tiny laser, since it's collimated, it's coherent light, so then it's much more easily focused, can be extremely dangerous in principle. Let's see how, for example, wavelengths are affecting different parts of our eyes. So if you're in the UV, you see that 100% of the light is absorbed by the cornea. Okay? So then if you're using actually UVB or UVC, in principle your retina is safe, but your cornea is in big trouble. Okay? So then we will see what are the, let's say, the diseases or pathologies that can happen in that case. Then when you get closer to the visible range, you see that just imagine that the laser is coming from here and this is penetration in the eye, right? Which is pretty, horrific, but anyway. When you get closer to the visible range, you see that penetration goes and goes and goes, and then this is a pretty obvious thing. When you get to the visible range, by regulations, visible range is defined as 400, 700 nanometers range, okay? When you get to this range, you see that almost all the light is going to be focused on the retina. So then your big issue is regarding the retina, which is quite obvious. I mean, it's visible, that means we see it, so then it means the light must go on our retina, right? What it may be interesting is that when you go here, 800 is not visible, you see? but still, the retina is still absorbing light. And this is quite an issue, because in the visible range, you have what we call aversion responses. So we close our eyes, okay, as an average, 1/4 of a second. But we don't have it here, okay? In the near infrared, we don't have the same reflex. So that means that exposure time could be much higher in the infrared, because we may not even realize that the laser is in our eye, okay? So that's something that when you make laser risk assessment, you have to take into account, because you have to consider an exposure time. And in the visible, that's never going to be more than 1/4 of a second, but in this case, it could be 5 or 10 seconds, for example, okay? Then, I didn't do this graphics. This is something that came from international organizations. These are the damage, actually, to simplify, damage curves defined by the IEEE, I think, giving you, for example, in the UV, there's what is called erythemal damage curve, and it's peaked at 280, and then it decreases going closer to the visible. Erythemal damage is actually what? It's sunburn, okay? It's the equivalent to sunburn, to the cornea, okay? And it's, I never experienced that, luckily, but they say it's extremely painful, unfortunately. This is pretty curious. You see, this is already visible, and it's what is called blue light damage. So it's a photochemical damage in the visible. Blue light can stimulate photochemical reaction in the molecule, so it's able to break molecular bonds in biological tissue. So then it deserved a specific graphic for himself, blue light. And then when you go to the visible and near infrared, you see this is already blue light. It's also there. It's the same graphic. And then this is how the retina is damaged by the light. You see that it decreases in the infrared, but it doesn't stop in the end. And it goes up to 1.4 microns, okay? So even at 1.4 microns, your retina is going to absorb light, and it can be damaged by that. And let's have a look at this. Indeed, when you are in the UVB, UVC, you can have photokeratitis, as I told you. It's an inflammation of the cornea. It's actually sunburn, okay? Then when you get to UVA, you can have a photochemical cataract, so it's clouding of your eye lens. In the visible, of course, the vast majority of damage is given to the retina, and the same is in the near infrared up to 1.4 microns. So you can have retinal burn and also some problems with cataract. Then in this range, you go back to the cornea, actually. So the penetration depth is going to reduce when you go further in the IR. Of course, if you use a 1 kilowatt CO2 laser, then probably your issue is not only about the cornea, because it's maybe used to cut metal or something like that. So then it's going to be a bigger issue, okay? Now, this is quite interesting to me. This is the kind of interaction and so damage you can have by light, okay? So you can have photochemical damage, which is breaking of molecular bonds. You can have photothermal damage, which is actually heating. You can have photoablative damage, which means that the tissue is removed, so it's ablated by the laser light, but there's no thermal damage in adjacent tissue. And you can have photochemical interaction, which means that you reach extremely high temperatures in the tissue, and the thermal gradient is able to generate shock waves that damage the adjacent tissue, okay? So this is not only a matter of danger, this is something that is used in medicine. So if you see in this graph, you have the interaction time on the X and the irradiance on the Y. If you increase the interaction time, so you make laser interact more with the biological tissue, you can generate photochemical damage, and it's something which is exploited, for example, in some kind of cataract surgery. Photoablation, so you reduce the interaction time and you increase slightly the irradiance, is used, for example, in the PRK and LASIK surgery, so for to restore better vision. Okay, photochemical damage is something that is used in other kind of surgeries, and again, photothermal it's less used, but anyway, I mean, there's an application in medicine for every kind of damage. You know, whenever something is able to cut something, surgeons are happy, you know, so they're going to use it. And they find very, very nice ways to use it in the end. So instead, regarding the skin, we're gonna be pretty fast here, because the kind of damage is actually the same, photochemical and so on, because it's always biological tissue. But this is how different wavelengths are absorbed in our skin. And probably the most important part is regarding UV. Why this? It's actually for potential carcinogenesis in principle. So the range that can generate carcinogenesis is this. It's UVB mostly. UVC is mostly absorbed by the most external part of our skin. And UVA can cause actually erythema and sunburn and hyperpigmentation. It's actually another way to call, it's a pathological way to call the sunburn, actually. So then, this is regarding the skin, but we are going to be pretty fast here. Now, okay, we go back to regulations. Protective equipment. So, just focus here at the beginning. When you're carrying on risk assessments and then you need to protect people, there's a specific way of doing this. You have to prioritize. So the first thing you have to do in principle is having organizational and technical measures. What are these? For example, I would not allow into a laser lab everyone. I will just allow those people that are going to use it. That's actually already a protection measurement, because you're putting at potential risk only a limited amount of people, and all the other are someone you don't have to care about. Okay, so then this is, for example, an organizational and technical measures. Lights outside every laser lab, you're going to need a laser on. There's going to be a light saying don't come in, because here it's really dangerous, we got laser working here. Okay, this is kind of organizational and technical measures. If you can't nullify in principle the risk with this, then you have to go to collective protective equipment, which means enclosures. That's actually the easiest part. If you put your laser in a big box, and outside the box nothing is coming out, you're pretty okay. You just have to take care that if that box is going to be open, whenever it's open, the laser is going to stop. It's pretty easy electronics. You just have to have an interlock in that case, right? This is what is called collective protective equipment, because this kind of stuff is going to protect everyone, not only one person. And if you can't make it, as it often happens in, for example, university labs, you have to go then to personal protective equipment, which means mostly lab coats and mostly laser safety glasses, right? But you have to prioritize in this way. Now, just since you're probably going to use, or hopefully use, in any way, in any case, you're going to be asked to use them. Let's have a look at laser safety glasses just a bit, just to understand what's written on glasses. You're not going to see here, I'm sorry about this, but this is reported here, okay? So, on every safety glass that it's actually certified, you're going to find something like this. And let's try to make an interpretation of this. The first thing you're going to find is the range. Okay, wavelength range where it's going to protect you. For example, here, 180, 315, okay? But then, what kind of level of protection is going to give us. Second part of the label is this, type of radiation. So there's going to be 4 possible letters. One is D, I, R, M. D means that it's protecting from a continuous wave laser. So it means or continuous wave or pulses longer than 0.25 seconds. This is probably not the case, right? Then I, it means I'm going to protect you from long pulses. So pulses that last from 1 microsecond to 0.25 seconds. R means I'm going to protect you from Q switching, so it's about nanosecond lasers. So pulses that are staying in this range, 1 nanosecond, 1 microsecond. And then M stays for mode locked. So whenever you have a mode locked laser, so a femtosecond laser, very fast laser, it means that I'm going to protect you from pulses that are shorter than 1 nanosecond. So picosecond, femtosecond regimes. Then after this, you're going to find this strange number, which is not optical density. When you make your calculations, you took into account power, spot size, divergence, condition of scenario of exposure, and so on. Then you get a number which is similar to optical density. But this is not enough in the end, because for the law, you have to guarantee, not you, but the producer of glasses, have to guarantee that these glasses are also going to stand. They have to be able to bear this radiation for a specific amount of time. And this amount of time is 5 seconds or 50 pulses. Okay? So then, this is another number which is called the scale number, and it's in some way related to optical density, but it's not optical density. Okay? And you cannot know if this is correct. There must be a guy who told you, me actually, or my counterpart in the place where you're working. So, for example, if in the risk assessment it's written, you need to use, I don't know, 250 nanometers, and the minimum level of protection is DLB5, then this goggle here is going to be good, because DLB5 is lower than DLB7. So then this goggle is going to protect you in that case. But you have to find this in the laser risk assessments, which is carried on by other people, not by you, right? Okay, then this is quite boring in the end. Now, an example of the potential danger of a laser. First, let me explain to you these parameters. There are some laser safety parameters. MPE is the maximum permitted exposure. It means the maximum radiant exposure that I can release on the retina without giving you damage. Okay? Then accessible emission is the radiant exposure which is released on the retina by that specific source in that specific condition. And then this number, MPE excess, it's actually the quotient between the two. So then you understand that if this number is higher than 1, are we in danger or are we safe if this number is higher than 1? Who answers? It's easy. Come on. We are in danger indeed if this number is higher than 1. If it's lower, of course, this is straightforward, we are safe. In general, in safety, you consider that you have to go at 0.2 at least to consider safety conditions, okay? Not 1. But anyway, it is correct. Number higher than 1, danger. Number lower than 1, pretty good, okay? And then there are some other parameters, but we're not going to speak about this. This is the nominal ocular hazard distance. It means how far away I have to go to be able to look into the laser directly without having any damage. Okay, oh yeah, usually it's kilometers. It's kilometers usually, yeah. But if you have a highly divergent source, then it can become meters or in some case centimeters. For example, when you have a fiber that has a lot of divergence, it can become safe in a very short range. So, but usually, well, you have to calculate this, and you put it in risk assessment, and it's nice because sometimes it comes 300 kilometers, and it's, come on, but you have to write it. Anyway, This is an example I took from my labs. This is the most innocent laser that we have, okay? So it's a helium neon laser. It's considered just fresh water from almost everyone. 22.5 milliwatts. Then these are all the other parameters. Doesn't matter. I considered an operator distance of 0.5 meters, which is pretty standard. I mean, if you're working on an optical bench, you're going to be at about this distance from the source, okay? Now, if you see here, I plotted exposure time, so how long it stays into your eye. Then from here, it's nonsense because you're going to close your eyes, as I told you. But anyway, doesn't matter. Exposure time, and here the MPXS. So then, in all the exposure times that are higher than this, we are going to be in danger. And if you look here, this is about 50 milliseconds. Okay, so this guy is able to make damage in about 50 milliseconds. So 1/5 of the time required to your eye to react. Okay, and if you want to go to 0.2 MPXS, then you have to go to 20 milliseconds, which is non-human. Not even 50 is human, but 20 is even less human. Okay, so then, and this is probably one of the safest lasers that I've ever seen in a university lab. Okay, in a research lab in principle. Now, just to to complete the job, let's speak for just 1 minute, couple of minutes. Am I late?
No, you have a quarter.
Wow, so I was pretty fast. Very good. So let's speak about laser accidents and analyze them a bit. The first one is about a guy here in Italy in 2014. He was a 13-year-old guy who was playing with such a thing. Okay, so a laser pointer. As I told you, most of laser pointers are class 3R, so they can be quite dangerous. He was playing with this and he burns a part of the retina on the right eye and almost lost use of that eye. The left eye was also damaged in the end, but with glasses he may actually see. It's not going to be completely blind, but he was just playing with one of these. So they're pretty legal, okay? They are totally legal. And this is the point I told you. Actually, this kind of lasers can give you trouble in less than 50 milliseconds, but it takes you 1/4 of a second to close your eyelids. So then, this is quite impressive to me. This is even more impressive. This was a techno concert. It was a rave party in Russia in 2008. The organizer were making a laser show in the air, but what happened was that weather condition didn't allow to make it in open air. So then they had to close the venue. And unfortunately, they didn't take into account the reflection of the roof. So then these poor guys were just dancing all night, and they didn't even realize that they had damage. They realized the day after, and in the end, there were 30 people aged between 16 and 30 that had blindness or impairments to their. Actually, I don't want to scare you, but I have to in some way. So this is a quite horrific accident. Sorry, any question?
I will make them relax. You can make them nervous.
Okay, this is, in my opinion, quite impressive. Then let's go to research labs. Since I took this from a paper in photonics.com from this guy who's the laser safety officer in Berkeley, they are all US-based accidents. In principle, there's not much literature about this because most of laser accidents are not even reported because people don't even realize, they are scared. And actually, I understand why they're scared, because when there's such an accident, it's going to be considered, how do you say that in English? It's going to be considered a serious injury. So then there's
The whole laboratory will be closed.
the lab is going to be closed for sure. For quite some time it's going to be closed until they can make their survey, and then there's there's a process in the tribunal in the end for sure, because it's a serious injury. But then, so then there's not much literature about this. But let's look at them, because these are pretty common situations in laser labs. In this case here, there was an undergraduate student and professor using a dual laser system. There was one laser exciting particles and a second laser monitoring, right? So it's like palm probe principle. No, not really, but anyway, similar from that point of view. The professor was looking off axis and he saw the first laser, okay? But he was in a specific situation. Then he called the undergraduate student, and the student also looked, but they didn't realize that the second monitoring laser was on. And since the student didn't put herself, I think it was she, in the same position of the professor, but just slightly on the side, the professor didn't see the second laser, but unfortunately she saw it because it was in her eye in the end. And in the end, she had the laser had vaporized a part of her fovea. Okay, in this case, they just didn't check that the second laser was off. You can even be safe with one, but then there was the seconds, and once the damage is done, you're not going to restore it. Or hopefully, we hope we're going to restore it in some years with the retinal transplants, but not for the moment. Second accident, there was this guy observing fluorescence while a second scientist was adjusting the setup. This is also common. There's a guy observing what happens and telling the other guy, no, move left, move right, okay? And this is one of the most dangerous things, because in optical setups, you often have quite some meters of optical path, and just a slight difference in the angle or in the position can become a huge distance after some meters, okay? So then what happens then was that the guy moved it, and unfortunately the other guy had hemorrhaging and permanent vision impairments in both his eyes. In this case, the mistake was that it was an alexandrite laser, so he's not going to see it. It was near infrared. So then there was no point in not having glasses. He couldn't have seen the laser anyway. So then, in this case, laser glasses were obvious in principle. Last two, and then you're free as birds. This happens in Argonne. This was very unlucky, actually, I have to say. This guy had goggles, but he had a slight infection in his eye, and at a certain moment he moved the goggle to rub his eye, and there was some stray reflection from the table. This is very unlucky, but there's also some, we can learn something from this. You're working with the setup. In principle, it should be closed. I understand that sometimes you're not able to close the setup. You're not able to enclose because you have to work on that every 2 seconds. But the first important thing is that if you're not going to be able to enclose the laser or the setup, at least you have to check all the stray reflections that you have from your table. You cannot have 3 beams pointing at the wall at the end of your lab, okay? Which is something I've seen happening. It's something, I'm recorded, right? So never happened to me. I never did this. So.
I think they are going to be criticized before release.
Pardon?
They are going to be criticized before release. All the videos.
Okay. No, but sure, it never happens. So I never seen this, but unless. I was guest in I don't remember what lab, and I've seen it long year ago. Anyway, stray reflections are important. You have to block them. You cannot leave them free because you never know who's going to come in the lab. You're never probably going to remember that the stray reflection is there. So then you have to block it. This is extremely important. Actually, you can have a reflection from every single lens in your setup. So then there can be actually tens of possible reflections, and you have to check them all for sure, because that is the easiest way to get injured. then the last one is about, this guy was pretty, quite a good guy. He made everything correctly during the alignment. He put goggles, he put everything. Then he came back to check the laser and the experiments, and he said, come on, the only dangerous moment is when I'm aligning, right? I mean, it's when I move the laser. But you can have drift. You can have someone else who came into the lab and moved mirrors or whatever. Actually, he came into the lab without goggles because he thought it was a totally safe condition, and damage again. So, okay, these are, of course, these are all very unlucky situations, but accidents don't happen every day. So it must be an unlucky moment, for sure. If accidents happened every day, then, I mean, human beings would not even exist anymore in principle. So you need a lot of circumstances, and this kind of stuff is rare, but it doesn't mean that it's not happening, okay? It happens. Sometimes it's not reported, but it happens. Anyway, this was my last slide. Let me just thank Guglielmo Lanzani, because I have to keep my job, and so I'm really, I'm really grateful to him. No, he's really supportive in this activity. So then I really have to thank him. And then Ilaria Monaldi is the corporate health and safety manager in Istituto Italiano di Tecnologia. She's also very supportive. And this guy, who's my counterpart in our central lab in Genova, who's actually the guy I speak more to, because we have to, it's quite a complicated matter in the end. So then 4 eyes, it's better than 2. And 2 is definitely better than 1. So, so anyway, thank you for everything. If there are any questions.
Questions?
Yep.
Yes.
I have a question about the gimmicky lasers they commercialized the last Christmas.
Oh, I don't know about it. Well,
I
tell me the story.
It's a laser projector.
Mm-hmm.
That one is supposed to put outside. Then it shines a pattern on the walls.
Mm-hmm.
But I expect they've been used in some non-orthodox ways. Because I, for example, had some shine through my window and had to basically shut down a side of the house.
Wow.
And it wasn't mine, it was a couple houses further down the block.
Wow. Okay. I can tell you if it's, in principle, if it's safe for the risk assessments, you can even play with the laser directly in your eye. Okay. So then, it could be that that laser is as dangerous as street lights, but I cannot know. I mean, in principle, it should be measured.
So because it depends on if it's intact, or for example, maybe this Christmas it was safe, it gets thrown in a garage, and then next year we can say how it's aligned.
Oh yeah, that's another point. That's another point. That's another point. But yeah, true, definitely true. But just think that a misaligned laser will never give you more power than let's say a laser in well shape. Okay, so then of course let's say not maintained laser is more dangerous for many reasons, but luckily not from the point of view of power. So let's say, but anyway, it's something that should be addressed in principle by someone. Hopefully the guys who made it. But any other questions?
I would like to add something.
Yep.
For the students also, I will upload where Stefano's transparency have a video, safety video from Rutherford, so you can see visually whatever he said, and in order to notify. And I think that you should be somehow scared when you are using lasers in order to take all the precautions. Because as he said, you know, when you experience the damage, you are not realize it immediately, but probably you are going to realize it after a week, after days. So you should take all these precautions, and it's not only, you know, eye damage, it's also, you know, from chemicals. Don't try, you know, to maintain your laser by yourself. Or there are fire precautions that you should take.
Yeah.
It's, very powerful lasers. They have all these electrical connections. And also, I was surprised that one of the most essential safety measurements that they are taking is like, this lock-in. When you open the door, accidentally by someone, the laser is shut off.
Yeah, that's quite an important one. Not always you can make it, unfortunately, because in some cases, when, in principle, it is totally right. In principle, when the door is open, the laser should be shut down.
If someone, for example, violates the laser on, or he knows the
Yeah.
password to pass, the laser is going to be automatically shut down.
Indeed.
If you go accidentally inside.
Yeah.
Yes, sir.
You had any laser accidents here in the Polytechnico?
No, at least not to my knowledge. But I cannot exclude it in principle, because as I told you, sometimes they are not reported. But not to my knowledge, actually.
Most of the time, those accidents are not reversible. So if something happened to someone...
Oh yes, this is true, but just imagine that sometimes it may happen, since the eye is an amazing lens in principle, so then it's focusing pretty tightly, and the damage is going to be actually extreme, but very, very, very focused in a small area. So then,
10,000 times the amplification of our light for the visible.
indeed. So actually it may happen that in your retina there's a hole, and of course you know that, but in some way your brain could compensate for that, and in the end you're going to see pretty nice, even if you have a hole. Okay, so then, but sure, the damage is there anyway.
And what happened with the people that have that hole? They see like a black spot. Like a black spot.
Yeah, there's a black spot in your view. At the very beginning, from what I know, at the very beginning is pain, and also you see something white, and that's mostly because of thermal damage around. Since sometimes it's very, very high irradiance, it may happen that you also heat up the tissue around. So then you may see like a white spot at the very beginning. But then in the end, there's something that, just imagine how bad it is to look at this room and see all the room, but with a hole like this, totally black. In my opinion, it's really horrific. I mean, you don't want it, not for you and not for anyone. But
one more question.
Yep.
You didn't talk about it, but are there any treatments for people having laser accidents in the hospital?
we are trying to, actually. No, actually, not to my knowledge. I mean, in principle, for cornea, the only thing you can do is cornea transplants, which is not, it's not fresh water. And for the retina, as I said, we hope we can make something in a close future, but at the moment there's not. Do you know of any possible therapy about retina? He's a real expert of retina.
Like artificial. Am I right? in Sweden, in shopping.
For a small spot, you do not.
You don't do anything.
Saying, the brain is cancer and needs to. First of all, we do have a dark spot in our eye.
Indeed.
Because the optic nerve appears the retina and go back to the brain. So each eye has a dark spot due to the strange engineering with the reverse organization of the photoreceptor. So if you close one eye, and I can show you what you will see at some point, you don't see it, whether it's dark spot. No, you don't see it because the brain is correcting for this effect. Right? So we already have a dark spot and we don't see it. So I think most of the time, as you were saying, the spot is small and the brain is correcting, and at some point you don't see it anymore. Also because we always reconstruct the picture, right? So if something doesn't move, we don't look at it all the time. We have a frame in the brain which is there. When something is moving, there is a refresh. So, I mean, it's a very complex system that is able to correct. Of course, if the whole retina is damaged, then it's similar to macular degeneration retinitis pigmentosa. I can say that we can rescue vision in blind rats with our artificial prosthesis, but we still do not know what we can do in human. I will tell you in a few years.
Okay. So, but if you would like to see a nice laser show, come to a Greek basketball game. You do the EuroLeague, and you can see the laser pointers that they are playing around. So, let's thank the speaker again for the nice talk.
Thank you.